Welcome back to this online NPTEL certification course in molecular rearrangement and reactive intermediate. Last couple of classes we have learned about the carbocation, we learned about their structure, their reactivity and various different rearrangement reaction using carbocation. In today's class we are going to learn about carbanion. So we are going to learn about first the structure and stability of carbanion. We are going to learn about the correlation of the pK and the carbanions, their different pK, their stability, their reactivity. We are going to talk about some of the rearrangement reaction as well. So if you talk about the carbanion, then the first thing is comes to our mind that the carbon with a negative charge. So now if you think about, so if you talk about the carbon with a negative charge, then if you remember when I was talking about carbocation, I told you from this methane, if you get as a H minus, then you generate this CH3 plus. Now if you from methane if you take a H plus, then you generate CH3 minus. So this will be the methyl carbanion. So now you can see the carbanion what will have a carbon with a negative charge, it attached with it forming 3 other bonds. Okay. So totally the carbon having the 8 electrons, 6 are the bonding electrons and then there will be 2 electrons which are not bonding electrons, and then carbanions are much more reactive species. And so you can see there are a lot of different type of reactions which are done with carbanion. And now we are going to talk about different type of carbanion. So if it is happening through this as I said from methane, we call it methyl anion. So now if you talk about this methyl anion geometry, so it is carrying a sp3 hybridization. Okay. So it has a pyramidal shape here. So it has this electron pair which is carrying one of the sp3 orbital actually have this electron pair there, and it is forming the 3 bonds with the 3 hydrogens. Now once you go to the vinyl anion, now this will be a sp2 hybridized. Once you go to the acetylide anion, it will be sp hybridization. So what is happening in case of sp2 and sp hybridization, so they are actually have a planar structure, but in case of sp3 it has the pyramidal structure. Now we are going to try to understand about their stability. Now going from sp3 to sp2 to sp, what is happening, the percentage of S character is getting increased. As the percentage of S character getting increased, what is happening, the electronegativity of the corresponding carbon is getting increased. As the electronegativity of the carbon is getting increased, it has a tendency to attract the electron density more. As it is stabilizing the electron density more, that is why this carbon will be more stable compared to this one, compared to this one. Now we can see, we can talk about the stability of a primary versus a secondary versus a tertiary carbanion. So what is happening here, going from primary to, so this is a primary to a secondary to a tertiary, what is happening, we are seeing that the stability actually getting decreased. So going from primary to secondary to tertiary, or if you say from tertiary to secondary to primary, what we are seeing, the stability getting increased. As the number of methyl group is getting increased from primary to secondary to tertiary, what is happening, the plus I effect will be more. As number of plus I effect is getting increased, the electron density will be more on this terbutyl carbanion. So as the more electron density will be there, it will be more reactive, but it will be less stable. Now once you bring some sort of a double bond or a phenyl ring like a benzylic or allylic, in that case we have learned in case of carbocation also that there will be a stabilization through resonance. So we can able to draw the resonance structure here. So to show you that allylic carbanion will be getting stabilized through this resonance structure, and we can able to draw the resonance structure here as well. Very similarly for benzylic carbanion also the resonance structure is giving this corresponding benzylic carbanion better stability. Now once you go from a monobenzylic like this one, dibenzylic and then tribenzylic, what is happening, going from mono to di to tri, the stability actually getting increased. Why that is happening? Because the number of resonance structure to stabilize this carbanion is getting increased from a mono to di to a tribenzylic carbon ion. So, now we are going to talk about the carbon ion where getting stabilized if there is a electron withdrawing group which is attached to this carbon ion. So, here we have a carbon ion, okay, which is alpha to the carbonyl group. Okay. We have already learned this type of chemistry that once you have carbonyl group, you treat a base, you generate this alpha to the carbonyl carbon ion, and this is getting stabilized through the carbonyl group because through the resonance. It could be other electron withdrawing group like nitro. Nitro can also stabilize this corresponding carbon ion. That means if you have electron withdrawing group, then that particular carbon ion will be more stabilized. Stabilization can be done by sulfur and phosphorus. So, we have learned about the sulfur halide and the phosphorus halide chemistry. If you remember, at the time we have learned that the sulfur or phosphorus will be going to carry a positive charge and the corresponding carbon which is attached going to carry a negative charge, and that negative charge will be stabilized by sulfur or phosphorus because as they have the vacant d orbital. So, this electron can be transferred to the vacant d orbital to stabilize. Then the stability through the aromatic carbon ion, as I mentioned that if you have a benzylic or some sort of aromatic, it has a part of aromatic things attached, then it can also stabilize through the resonance. Also, if it is have a something like that, if the carbon ion will be part of a aromatic system, okay, in that case like this cyclopentadienyl carbon ion, so which is getting stabilized, it is a 6 pi electron system is getting stabilized because of the gaining aromaticity. Now, we are going to talk about some of these example here where you can see, although this is a a carbon ion here, but the problem is this is this is anti aromatic compound. So, compared to this one which is aromatic. Okay. So, aromatic will be a carbon ion which is actually forming aromatic compounds will be more stable compared to the other carbon ion which is forming a anti aromatic compound. Okay. So, the stability will be aromatic, non aromatic and anti aromatic. And now we are going to talk about the stability if you have a electron withdrawing or electron donating group. Suppose the carbon ion is formed here. Now the thing is, now in case of benzene ring, if the benzene ring will have attached with the electron withdrawing group versus electron donating group, what is going to happen here? Now depending on the substitution of the nitro group, you can see that in these cases where the nitro group is ortho to the carbon ion, is going to stabilize more through the minus I effect. So, now you can see there that in case of OMe group here, what is going to happen here? The OMe group can have a plus R effect and a minus effect. So, the plus R can actually destabilize the carbon ion and minus I is going to stabilize it. So, that is why you can see these particular compounds where your plus R is not operating, only the minus I is operating is actually more stable compared to others. So, now we are going to talk about the other important factor is called the pyramidal inversion of carbon ion. So, as you know, the carbon ions are isoelectronic to the ammonia, and we have learned about the pyramidal inversion there, which actually what happened is it actually goes for an inversion here where you can see the configuration which was here actually going to form the corresponding enantiomer after the pyramidal inversion. So, now we are trying to learn that while this inversion happen, it actually goes through a planar tangent state. So, that means if it is going through a planar tangent state here, that means this R1 and R2 has to get some sort of a planarity to go to the corresponding inversion product. Now, you can see here if R equal to H, the barrier for the pyramidal inversion is 2 kilocalorie per mole. Once R equal to fluorine, the barrier is 120 kilocalorie per mole. So, why such a difference in the barrier for this pyramidal inversion? Because during the transient state, as it has to achieve the planarity, there will be repulsion between this fluorine atom. As there is a repulsion because of the fluorine has this the lone pair which can repel each other, and that will not allow it to bring to the planarity. That is why the barrier is higher here. We are going to learn about other systems, also there will be a problem. So, now we are not talking about the lone pair repulsion, we are going to talk about some strain system. Like if it is a cyclopropyl anion, now you guys know that the cyclopropyl has a bond angle of 60 degree. Now this anion to go for an inversion, it has to achieve a planarity. To that it has to come to a angle of 120 degree, which will be very difficult, okay, to achieve that. That is why the cyclopropyl carbon ion mostly do not go for this pyramidal inversion. And here is an example here. If you can start with this particular chiral compounds and go for a metal halogen exchange to generate this corresponding lithium, this lithium is still making the retention of this configuration. It can able to trap with CO2 to the corresponding product. So what we are seeing that if you are generating a cyclopropyl anion, then it is going through a retention. We are not seeing a mixture of RNAs. Now I am going to talk about the types of carbanion. So there are several different types of carbanion. One of the very reactive class of carbanions are organolithiums and Grignard reagent. Okay. So organolithium and Grignard reagents are very reactive. They are very much unstabilized, because you cannot see there is any other group attached to them that which can stabilize the carbanion, and they can readily add to carbonyl and in many other functional groups, and they are not useful for SN2. Then I am going to talk about some of the stabilized carbanion like here, which is actually carbanion in the sp carbon. As I said, because of the higher electronegativity of the sp carbon, it stabilizes that carbanion, and it can be readily added to a carbonyl group and other functional group, and it can also participate in a SN2 reaction. The other one is very well known, which is the enolate anions. Okay. So enolate anions can be very much stabilized through this carbonyl group resonance, and now it can be readily add to carbonyl group and participate in various type of chemical transformations, and of course is go for the SN2 reaction as well. So now I am going to order these different type of carbanion with their pK values. So now I am talking about a pK of a base. So generally, if you know the definition of pK is actually minus log K, which is nothing but the dissociation constant of HA to A minus and H plus. Generally, we use pK to talk about that if we say have a pK lower digit, that means it is strongly acidic. In case of base, what we try to represent, that if a base is very strong, then the conjugated acid will be very weak. Like we are talking about a butyl lithium, which is a very strong base. Now its corresponding acid, which is the protonated acid, is butane, is a very weak acid. So it has a pK of 48. So you can understand it is a very weak acid. So that means that the conjugate base will be very strong. Similarly, there are the LDA, which is a very common base, we have seen, again have a pK of 38 because of the protonated form is actually a weak acid. Again for NHMDS and for alkoxide, which has a pK around 16. Okay. So what we are seeing here, going from this alkoxide to NHMDS to LDA, what we are observing? We are observing the pK getting increased, because what is happening, the base becoming stronger and stronger and stronger. And we can see here also that we have a methyl carbanion, ethyl carbanion, isopropyl carbanion and tert-butyl. What we are seeing here, the pK value getting increased, and as you know that as the number of methyl group is getting increased, there will be plus I effect will be more, so that this type of carbanion will be more electron rich and more reactive, okay, compared to them. And then there are other type of carbanion here. I told you that so this particular class of carbanion, which is actually in part of the aromatic system, which is getting stabilized through the resonance, and then we have a carbanion here which is in the sp on the sp carbon. Then we have some sort of a conjugations with the benzylic. Then we have this aryl carbanion and vinyl. So they are the more more reactive carbanion here. So going through this direction, what we are seeing the pK value getting increased and the reactivity is getting increased as well. And this is another comparison here. Why I am putting these slides here, because this is another way to understand that generally we use pK for showing for acid, like you can see the carboxylic acid has a pK of 5. But now if you try to understand that which type of base we need to use to going for a deprotonation, then we have to try to correlate the pK of this type of compounds with the corresponding base. So suppose we want to use deprotonated nitromethane, so we know a nitromethane have a pK of 10. Okay, that means we need to find a base which will be lower than pK or close to that, which can able to deprotonate that. Very similar thing for amide anions. And then we have learned about the acetaldehyde and acetone, which you always use for different type of reactions, and of course we can use, we have a large number of base we can use for this type of deprotonation. Even using alkoxide or using the HMDS, LDA, which are often used for this deprotonation reaction. Here I am going to show you again the same thing which I was telling here, but the important thing is if you have a 1,3 dicarbonyl, then the proton here which are very much acidic, because once you abstract this proton, then the corresponding carbanion is getting stabilized here, because there are present of two different carbonyl group here, because that is actually stabilizing the corresponding carbanion which is forming here. Okay. So that in that case you can use a sodium ethoxide, that will be enough to abstract this proton, because that will have a pK in the range of 16. Then you have acetylene, like a phenylacetylene. Now this acetylene proton has a pK around 26. That means now you have to choose a base which have a pK. You can see you have to choose a base which have a pK more than that. That means you have to choose a base which will be something like N-butyl lithium, which can able to abstract abstract this proton. Okay. Of course you can also use a LDA to abstract this proton as well. Now we are going to talk about what are the different methods for the formation of carbanion. So here you can see that we have learned about these type of things, that from acid, once you heat up, particularly from this beta keto carboxylic, so beta keto acid, we call them beta keto acid. So beta keto acid, once you heat up, what is going to happen? It is go from a decarboxylation to formation of this corresponding ketone. So that way what is happening? We are generating a carbanion here, which is getting protonated. Then there is another method where you can add a nucleophile to a alpha beta unsaturated compounds. Like once you have alpha beta unsaturated compound, like you have a alpha beta unsaturated compounds, where you are adding a nucleophile. What is happening here? The nucleophile can attack here, and if you try to write there, that you will be generating a O minus double bond and a nucleophile here, which can come back and generate a carbanion here in the alpha position. So of course which can get a proton or something here, but so I am talking about generation of this type of carbanion after addition of nucleophile. There is an example given here which I was trying to tell you in the previous slide to generate a carbanion. Then the other very common method we use in the laboratory, generation of organometallic compound like organolithium, like RLi, RMgX, then R-zinc X, and then of course the organocopper and all these different things. So I think what is happen in case of organolithium, you generally see a metal to halogen exchange happens, okay, from corresponding alkyl halide. So we are going to talk about this type of organolithium, organomagnesium in very details towards the end of this course. We have a particular module which is dedicated for this synthesis and reactivity of organolithium, magnesium and corresponding zinc. Okay, so here are other method, as I mentioned, that you can do a deprotonation from acetylene to generate a corresponding carbanion. There is other type of method. So we learn about the haloform reaction. So in the haloform reaction, what we have seen, that there is a generation of some sort of a species like Cr3 minus. What is happening? This particular group is actually getting out, taking this 2 electron pair, this Cr3. Okay. So what is happening in case of haloform reaction, in case of iodine and base, this CH3 will be replaced by Ci3. So now it is the base can attack here, because it is getting very reactive to get rid of this as a Ci3 minus. Okay. So that is in case of haloform reaction we can generate this type of carbanion species. So now there is a question in the GATE exam, that among the following compounds, the one that undergoes in deprotonation most rapidly in the presence of base. Okay. So now if you see this A, B, C and D, in case of A there is 2 carbonyl compounds. So in case of B there is a 2 esters here. So we are talking about these protons, because if the deprotonation happens, then it is going to abstract these protons. So now if there is 2 esters versus 1 ester, 1 carbonyl, one type of a double bond. So then what is happening here? So this will be allylic versus a, this will be allylic versus a carbonyl group here. So, now what is happening, this will be actually going to, so this is the compound which undergoes the deprotonation faster, because this carbonyl will be getting more stabilized through this 2 carbonyl group. Then among the following acid which undergoes faster decarboxylation, as I told you, you have to look for a beta keto acid. That means you have to look for which one is a beta keto acid. If you see, this is the one actually a beta keto acid, as I told you before, the beta keto acid only goes for decarboxylation, not the alpha. If you heat up alpha keto acid, it will not go for decarboxylation. Then there is a question here that if you have this 1,3-dithione, which you always use for protection of carbonyl group, for doing some other transformations. So, what is happening if you make this 1,3-dithione, then we have to try to understand there will be, in this particular case, there will be axial and equatorial proton. Now, which one is more acidic? You can see the equatorial one will be the more acidic. So, that will form the corresponding carbanion, because this carbanion is getting stabilized, giving electron density to the sigma star orbital of this carbon sulfur bond. So, this is the sigma star orbital which is getting electron density from this carbanion. Then there is another questions in the exam, which will be the correct order of pK of the following compounds X, Y and Z. Now, if you look into X, Y and Z, so one thing you have to try to understand that in case of X, it is just going to abstract this proton to form this type of carbanion. So, what we want to see, first we have to find out which will be more acidic. Which will be more acidic, the pK will be low, and which will be less acidic, the pK will be high, and then we can order them accordingly. Now, if you think about this particular carbanion, which is the Y, here after abstracting this proton to generate anion, which will be getting very stabilized here, because there are 5 cyano group here which is stabilizing that carbanion. So, that means if you so this proton will be highly acidic. So, that means this will be one which will have a, if you try to compare the pK wise, the pK will be the lowest. So, that means this is the one which will be the last, and then if you compare among these two. So, what is happening again, if you compare X and Z, in case of X, this H is attached with the nitrogen. So, you have to understand if the X, if the hydrogen attached with a atom like nitrogen or oxygen which can stabilize the corresponding carbanion with having a carbonyl group attached with it, then it is going to be the one which will be the next acidity. That means this will be the number X here, and then the next will be the Z. Okay. So, this will be the right answer. The correct order of acidity of the following compound, here they are asking about acidity, not pK. So, you have to be careful what they are asking. If they are asking acidity, we will order them. If they are asking pK, then we have to order them accordingly. So, based on acidity, now first thing is we generally learn that if you compare acidity, we have to go to corresponding carbanion and find out their stability. Now, if you find out this carbanion, of course, this is a aromatic compound, this is anti-aromatic compound, and this is also aromatic. Now, if you compare between these two, then you can see this is aromatic, but there is a negative charge which is getting stabilized because of this CF3 group here. So, this will be the one which will be the which can able to which will be the, I think this is the proton will be highly acidic. So, the order will be A, C and B. Now, we are going to talk about the reactions of carbanion as an intermediate. Of course, we are going to talk about a lot of these reactions of corresponding Grignard and lithium, as I said in a different module. But again, these are very reactive, add to a carbonyl compound to form this type of tertiary alcohols here. It can add to a ester. Once you add to ester, not only single methyl magnesium works, it actually 2 of them add here, because it first forms a corresponding carbonyl, then it another methyl magnesium chloride attacks here to form this corresponding alcohol. It can go for a substitution. If you have a carbanion, it can go for a substitution to form this corresponding product. And then I think there will be a lot of chemistry which was done, of course, using the enolates, which is the first it will be abstracting this proton, as I was telling you, and to formation of this. So, once it is forming from here, once it is going for the corresponding enolate, there are several different transformations, like it can go for a aldol condensation after reacting with the carbonyl compounds. It can go for a Michael addition. So, it can go for a Michael addition to this alpha beta carbonyl compound to go to this corresponding product. It can also go for a Claisen condensation here to reacting with these corresponding esters. So, there are different type of transformations of this enolate, which can be which is not cover this course. There are other NPTEL lecture you can find out, which actually talk in details about enolate chemistry. So, in this class actually I am going to talk about also about this reactivity, which is using this type of ylides. So, if you have a silicon and phosphorus ylide, then what is going to happen, that can add to the corresponding carbonyl compound and forms this product after the addition and condensation. And then the other reaction called rearrangement reaction, I am going to spend some time there in the next lecture and talk about various rearrangement reaction using corresponding carbanion. So, in this class I try to talk about the carbanion stability, and then which one will be more stable, which will be less stable, and then I talk about the different method of generation. And in the next class I am going to talk about more about the rearrangement. And these are the reference very similar books which I mentioned in the previous class. And thank you for coming to the class. I am looking forward to see you guys in the next class.